So hello, my name is Hahn, as already mentioned. I'm working in Group of Plus 11 at the University of Stuttgart, and I'm presenting the work on behalf of my colleague Ghareeb Falazi, which can't be here today, on transactional properties of permission blockchains. So before I go to the motivation, how we can actually kind of identify and discover such transactional properties, I first want to give a short recap of background because the paper is about two things, replicated database systems as well as blockchain systems. So for replicated database systems, so classically users, so we have a network of nodes that share a replicated data set, which is kind of synchronized across the nodes. And whenever a user issues a new transaction by sending a corresponding request to one of the nodes, for example here to write X to a new value, this transaction is distributed to the other nodes, and whenever the user decides to commit, this commit is implemented in a way that, for example, a corresponding consensus protocol like two-phase commit is used, but this requires trust in a single entity because the coordinator, which is node 1 here, actually, the other nodes have to trust this node to agree to commit the transaction and keep a kind of consistent state in all nodes. And if we go to blockchains, so there are two flavors or two types of blockchains. One is permissionless blockchains or public blockchains, and the other one is permission blockchains. And here we have a large set of nodes that are independent of each other. And for example, user A can send a transaction request where the actual transaction program is located within or executed within the blockchain itself. And this is then broadcasted to the other nodes by corresponding gossip protocols, for example. The same goes for user B with another transaction request, which is also broadcasted through the network. But this will potentially lead to different reasons that potentially different nodes come to different order of transactions. And therefore, we need some kind of consensus protocol that agrees upon a certain order without the overall network in order to reach a consensus and to have the same consistent state in all nodes. So whether say, okay, first transaction A and then transaction B, or vice versa, first transaction B and then transaction A. And therefore, corresponding consensus protocols are used. For example, so we have a set of users, a set of classical nodes, and a set of so-called validator nodes, which in public blockchains or permissionless, they also call miners. And they actually reach a consensus. For example, here they decide on first A, then B, and this consensus is then distributed to the other nodes of the network so that a consistent state is reached. So for permissionless blockchains, as I said, they're open for anyone. So they're users, regular nodes, as well as these validating nodes I already mentioned. Mostly they rely on so-called proof of work consensus protocols, which has kind of some drawbacks. So they're either slow because they are periodically putting multiple transactions into one block and then validate these blocks of transactions. So they commonly have a throughput, let's say, about 7 to 20 transactions per second. This mining also has a high power consumption and was also, especially in business scenarios or where we have GDPR private data, for example, there's no guaranteed data confidentiality because the network is open for everyone, so everyone can participate, read out data, and issue transactions. And they are also not ACID, as for example, research by Professor Tai screw. So they have a paper where they say it's not acid, it's even not base, but it's salt, which means that transactions that are committed are not reach a kind of finality, because they could be revoked afterwards if the blockchain is forked. And yeah, so this is really bad in kind of a business context, because if we agree to collaborate and then we both kind of the transaction is committed, and at a later point in time something is revoked because of this yeah, principle here. Yeah, so there is no kind of final transaction state. To actually improve this kind of drawbacks, the notion of so-called permission blockchains was introduced, where we have a restricted participation set, which means we have also users, regular nodes, and so-called validating nodes. The difference is that this node set is predefined upfront, so the network is kind of closed, because all users participating agree who becomes a validating node and who becomes a regular node. And therefore, because of these kind of access control mechanisms and vice versa, and other related things, data confidentiality is inherently guaranteed. Because it can be specified on a fine-grained level who is allowed to read which data and who is allowed to issue transactions and so forth. And because of this fixed set of nodes, which is clear upfront, so-called Byzantine fault-tolerant consensus protocols can be used, which are way more faster performance-wise, because they can do more than 1,000 transactions per second. They also require lower power consumptions, and they guarantee transaction finality. So the motivation of this work is, so if companies, businesses actually think about using blockchain technology to actually collaborate with each other, so we have here this kind of, these permission blockchains seem to provide a promising mixture of performance as well as trust distribution. But the problem is that they normally don't run isolated, so companies need to interact with these systems using their existing systems to actually achieve a business goal. And therefore the question is, if now a company system architect decides to use these kind of permission blockchains, what are actually the transaction properties, transaction processing properties that are guaranteed by these permission blockchains? Therefore, the following methods applied within the paper. So first, based on replicated database systems, corresponding prominent transactional processing properties are identified from literature. Then based on these, they are analyzed for 9 prominent permission blockchain systems, how they actually fulfill or achieve these guarantees. Then the resulting properties are determined and categorized as a final outcome of the work. So as I already said, so permission blockchains can be seen as some kind of an evolution of both public blockchains as well as replicated databases, where here we kind of add data confidentiality, and here we add trust. So the idea of the work is, as I said, treating permission blockchains as kind of replicated database systems. Here's a list of correctness criteria. I won't go to all of them. So the first 4 are regarding data consistency, and the second one is how transactions are processed. And here's just an example how the analysis of the different blockchain systems is done. So here, for example, for Hyperledger Fabric, and here we can see the transaction processing flow, which is already quite complex. And based on that, the different 9 systems are analyzed, and these characterization properties are evaluated. And here we can see 2 large coarse-grained clusters, where one actually guarantees us data consistency, not data consistency, so transactional finality, and the other ones do. And we can even go a little bit more fine-grained. For example, the purple systems here guarantee session consistency, while these do not. And here we have different architectures, so where's actually validations performed like in a kernel-based method, so within the blockchain, or by middleware, and same for concurrency control. So is it possible to have just serial executions of transactions as well as parallel, having more sophisticated concurrency control mechanisms? And to conclude my talk, so permission blockchains can be analyzed by comparing them to replicated databases. We see classes of systems that provide properties which are similar to replicated database systems, and other ones which are similar to public blockchains. And as I said, transaction finality is the most important factor within these systems to actually guarantee database-like transaction processing capabilities. And there's also room for improvement, as we can see by the findings, because more sophisticated concurrency control mechanisms could be provided, as well as guaranteeing session consistency. Thanks a lot.
Thank you. I think it was fair to give him 2 more minutes because he doesn't present his own work. So now thank you, but no time for questions. Now to the last talk for today by Michael Oster, the Center